All right, hello and welcome everybody to Recitation 8 for MAE 242 Intro to Fluid Mechanics. Today we'll be covering topics on Buckingham Pi Theorem and things like that, like non-dimensional number matching, stuff like that. It's pretty easy. It's pretty much a continuation of outcome one. If you guys were good at outcome one, you'll probably be pretty good at this one. How much Buckingham Pi Theorem have you guys talked about so far? What? Like a lot of it? A lot of it? All right, sweet. All right, so I'll kind of gloss through this quite a bit anyway. Um, it's a pretty quick one. There's just two problems, and the key is written really well. So don't overthink it. Just go check back with the key if you need to see something. I'll also add little anecdotes as I go, as usual. All right, so for this first one, for design purposes, the drag force on a large 100 centimeter, which 100 centimeters is just a meter. All right. I don't know why they didn't just write 1 meter. Um, Anyway, hey, can you be a little quieter back there, please? Anyway, balloon moving through the air. Yeah, we want to measure. Okay, yada yada. For design purposes, the drag force on a large 100 centimeter diameter balloon moving through the air is required. A scaled down spherical model with diameter 5 centimeters is tested in water at 20 degrees Celsius to determine the drag. The drag of a sphere placed in a fluid stream is dependent on the diameter d, velocity v, density rho, and kinematic viscosity nu. Part A, determine the relationship between uh, the dimensional drag coefficient, and the above parameters. And B, if the balloon is rising in air at 3 meters per second, determine the sphere velocity in water. All right, so first off, whenever you're doing any sort of Buckingham Pi Theorem stuff, you just want to straight up list the parameters that you're dealing with. All right, so let's get the parameters going. And so we were given that we have some. So it is dependent on the diameter d, velocity v, density rho, kinematic viscosity nu, and then some drag force, so we'll call F, right? I think the key has it as D, like bid D, but that's kind of confusing. So I'll write it as F. All right. And now, what are our dimensions? What are our primary dimensions, right? It gives us water at some temperature, but temperature is not actually part of this. These parameters are all MLT, right? It's just, L over T, M over L cubed, yada yada. So our main dimensions are M, L, and T. Now for the pi groups, our non-dimensional pi groups we're gonna form, all right? How we know how many we want to make by taking P minus D, right? And so we have 5 minus 3 equals 2 pi groups. And we go, all right. So now we're gonna start making these non-dimensional pi groups. And so to do that, we're gonna need to know the actual dimensions of each parameter, right? So let's write all these dimensions down. Diameter is just some length. Velocity is just some length per time. Density is, something like that. Kinematic viscosity is that. And then force is, right? And so now you go, we need to pick 3 repeating parameters, right? And how do we do that? So there's really 2 huge rules that you have to follow when doing these. The first one is generally you don't want to pick the repeating parameter that you're like you don't want to pick the parameter that you're trying to measure as a repeating parameter. So in this case, like ultimately we're going to be expressing some like drag force coefficient in terms of these non-dimensional numbers. So obviously we don't want to pick the drag as a repeating parameter because you'll be like changing it around as you go, and that's just clunky and annoying and it won't work. And then the second bid rule, the actual bid legit rule, is the repeating parameters that you pick. You cannot form a non-dimensional group inside of themselves, right? You can't, if you were to if you were to pick 3, oh, and I'm picking 3 repeating parameters, because that's the number of our dimensions, right? 3 and 3. You pick 3 of them. Um, you should have gone over that in class with you, whatever. But they can't make a non-dimensional derivative themselves. So they just get stuck in an infinite loop when you're trying to make everything non-dimensional, right? Because if two of them can non-dimensionalize each other, you'll get stuck with exponents going all crazy because they just keep canceling each other out and you won't know when to stop. So um, when there's just like five of them like this, you can just look pretty easy. So like we just said, we don't want to take this drag force, right? So that one's already off. And so now you look at these remaining ones and you go, well, diameter just has an L, velocity has an L and a T. So those two would be a good choice to put together, right? Because you can never get rid of that T with just that L. And then rho, you've got an M and an L cubed in the bottom. Well, neither of these other two have an M. So perfect. No, no combination of these three can make themselves non-dimensional. So boom, let's put those. Rho, D, and V. Right. And so now we're going to be solving for our kinematic viscosity and F. All right. So pi 1 will correspond to kinematic viscosity. So we take nu times rho to the A, V to the B, and D to the C, right? And we want to get these dimensions to all cancel each other out. So what we want to do, we want to take, L squared over T times M over L cubed to the A, L over T to the B, and then just an L to the C, right? And so now you set, you go, all right, so let's look at our M's first, right? Our M terms. So in the first one, we have zero M's. So then we'll get zero equal. So, this first term and the kinematic viscosity term, we have no M's. So zero. And then we have a plus A, right? Or yeah, plus A. And then, plus zero, plus zero. So A equals zero. It's pretty easy. Now let's look at the L's. Right, again, we have zero. We're going to make all those exponents equal zero. So L's, we have 2, and then minus 3A, which is actually just 0, but whatever, plus B, plus C, right? And we've got that system, whatever. And then T's. Let's look at the T's. We have 0 equals -1, right? Plus 0 minus B, right? So we get B equals -1. Ultimately, C also equals -1 if you go and solve that out. So for our first pi group, we have pi 1 equals nu rho to the 0, v to -1, d to -1. So pi 1 equals nu over v d. Or okay, so this is technically the legit answer. But if you're slick, right? If you're slick, did you guys talk about Reynolds numbers at all? Talk about what a Reynolds number is? Yeah. All right. So Reynolds number is rho v d over mu, but nu equals mu over rho. So you can also write this as pi 1 equals 1 over RE, right? It's just inverse. It's the inverse of Reynolds number. Or since it's all the same and everything's already non-dimensional and the inverse of a non-dimensional number is still non-dimensional, right? You can just say pi 1 equals RE, right? Any of these will work. It's all non-dimensional. It's all cool, right? Everything's fine. Okay, any questions with that part? Just algebra, making everything cancel itself out. Pretty chill. Cool. All right, now moving to pi 2, it's same thing. So this one corresponds to the drag one, the F. Well, same thing, rho to the A, V to the B, D to the C. Same thing. We have ML over T squared, M over L cubed to the A, L over T to the B, L to the C. And I'm not going to math this whole thing out. Just it's literally the same thing. You just form a system of equations. It's not hard. It's just linear algebra. Go plug it into a matrix if you really need to, but it's not difficult. And either way, this is a classed one anyway. If you have a force and then a rho v and some, a density, a velocity, and some length, you'll get a equals 1 or -1, I guess. B equals -2, C equals -2. All right. So ultimately, you'll get pi 2 equals rho v squared d squared, which this is like the classic drag coefficient right here. If you take like an arrow class, a lot of times you'll see instead of like a d squared, though, you'll see like an area there because a distance squared is an area. And then a lot of times you'll see 1/2 rho v squared. That's dynamic pressure. You always have some whatever force you're talking about up top. But yeah, this is a classic drag force coefficient, whatever you want to call it. It's all the same. So now, what we actually want to do, right? We want to determine the relationship between the dimensional drag coefficient and the above parameters. So basically, all you want to do now is we know that pi 2 by definition is a function of pi 1 because everything's non-dimensionalized with respect to each other, right? So you can set, everything's proportional to each other, right? And vice versa too. You can say pi 1 is a function of pi 2. You can flip flop them. It doesn't matter. Everything, like I just said, everything's proportional. Everything's non-dimensionalized with respect to the same stuff. So it's cool. So I can say f rho v squared d squared equals some function of nu over vd or 1 over Reynolds number or Reynolds number, whatever you want to call it. Cool. And so we can take this one step further and say f is, rho v squared d squared times some function of nu over vd. If you feel so inclined, it doesn't really matter. Either of these forms would work. These two would also work. We've established the relationship. That's all we want. Okay, so it's pretty easy. Now part B is super, super easy. All right. It's literally so for part B now, what we're going to be doing is we're doing what's called, like non-dimensional number matching or, dynamic similarity matching. All right. We know these two problems are dynamically similar and everything's non-dimensional, so we can set each pi group equal to each other and make some money. So we say B, if the balloon is rising in the air at 3 meters per second, determine the sphere velocity in water. All right. So what we want to do, we want to set these pi groups equal to each other for the prototype, right? And what's the prototype? The prototype is the actual thing you're like launching. So it's the big balloon rising in the air, right? And then the model is the smaller thing we're putting in the water, right? The scale model that's like 5 centimeters or whatever, right? 5 centimeters, that's the scale model. And so we want to get the velocity of this model. And so for part B is what we can say. We can say, B. We know that everything's all dynamically similar. So we can say, okay, well now which pi group do we want to match? All right, which pi group would get us the most information? Well, if we look at pi 2, we've got some force divided by, density, velocity, diameter. Well, we want to solve for our velocity, and we know density and diameter, but we don't know a force for either of them. So we can't use pi 2. But with pi 1, it's kinematic viscosity over velocity, diameter. And we know, for both of them, we know the kinematic viscosity and the diameter, and we know the velocity for one of them. So hey, let's use pi 1, right? That's the logical thing to do. It's the only thing you can do. So we know pi 1 of the prototype equals pi 1 of the model. All right. And now the only thing is just figuring out which one is the prototype and which one's the model. Well, I just told you which one's the prototype and which one's the model. Usually it's pretty obvious. So we can just keep going. So we can say prototype over. Where this velocity of the model is what we're trying to solve for. So now we're given all this stuff, right? I mean, it gave us all this junk up here. This is what we worry about. So we can say, It's like 1.516 equals. All right, go solve for the velocity of the model. Just very basic algebra. Vm equals like 3.97 meters per second. All right. See, not too bad. Pretty easy. The hard part is just making sure everything's non-dimensional, which you can check that anyway. Okay, just go back, make sure everything cancels. Right, go do the dimensional analysis if you're in a pinch. You already passed out to one, hopefully. I imagine. I would hope so. Whatever. Yeah, this stuff's not too bad. It's just basic algebra after you get to that point. Um, just the only thing I really see people mess up on is like figuring out which one's the prototype and which one's the model. Just it'll usually tell you in the problem statement. Just read carefully, okay? It's not that hard. Or like someone will flip one coefficient and not flip the other. If you do something to one thing, you got to do it to the other. Everything has to be consistent. Also, units don't really matter in this case. As long as the units are consistent between the two things they're comparing, it doesn't matter. Like we could have had this in miles per hour and everything else in centimeters and whatever. It doesn't matter. As long as it's the same thing between the two, it doesn't matter. By convention, it's nice to keep all the units in the same thing, but it doesn't matter. Cool. Anyway, any questions there? Pretty chill. Pretty chill. All right, sweet. There was a part C to this problem, but it's not like part of the problem statement. It's in the answer key if you see it. It just gave us like it gives you the drag on the model and it asks you to find the drag on the prototype. So it's the same thing, right? You found the velocity of the model. All right, go plug it into pi 2 and compare pi 2s to each other. Same exact thing. It's not very tough. All right, now problem 2, pretty much the same thing. So we're not even like comparing anything. We just have to find the pi groups. So let's do it. And I'll go really fast with this one because it's really like the same thing. And I'll show you, I'll kind of show you how to do this by inspection, right? If you just get good enough, you can just kind of look at them and do them. But anyway, so problem 2, a fixed cylinder of diameter d and length L immersed in a stream flowing normal to its axis at velocity u will experience zero average lift. Shocking, right? But however, if the cylinder is rotating at an angular velocity omega, a lift force F will arise. And that's true. That's true. That's a big arrow thing. All right. If you go take a hardcore aero class, you'll go see why that is. It has to do with circulation and whatnot. It's pretty interesting, actually. If you're down with stuff like that. But anyway, yeah, lift force F will arise. Fluid density rho is important, but viscosity can be neglected. Formulate this lift behavior as a dimensionless function. So we're just finding the pi groups. So same thing. Let's get our parameters going. Params. What are our params? D and L for sure. Also have some velocity U. Some angular velocity omega. Some lift force F, and viscosity or density. Right. So we got 6 of them. And then what are our primary dimensions? What are our dims? Just MLT again, right? So we're going to have 3 repeating parameters. And then how many? P minus D. We're going to have 6 minus 3 equals 3 pi groups. And I guess I'll write the dimensions down for all the stuff. It'll take 2 seconds. L is obviously a length. U is a velocity. Omega. What's omega? Omega is like radians per second. What's a radian? It's already non-dimensional. So it's just 1 over time. That's really the only tricky one in this. Force is just a force. Rho. All right, so now which 3 are we picking? Pretty much whatever you're given, some sort of like, you want to find some sort of force, right? And you've got all this other stuff. and you've got like a density, a velocity, and a length, just pick rho, u, and one of the distances, one of the lengths. You'll be fine. That's kind of a life hack. I wish they would have put a different example on here though, so you would have seen like a different set of repeating parameters, but it's all the same. So pick 3. Again, we're just gonna pick rho, u, and pick D, I guess. Doesn't really matter. You could have picked L or D. Does not matter at all. All right. So now solving for omega, L, and F. Right. So first one, pi 1. I'll call pi 1 the one that corresponds to the length because it's really easy. And I'll show you just how to do this by inspection, right? It's literally just logic. So we got L, rho to the A, U to the B, D to the C. Obviously, if you just put A and B equal to 0 and have C equal to -1, you get L over D, which is non-dimensional. Boom. Don't even have to do any work for it, right? Boom. It's a real tough one, L over D. All right, pi 2, slightly trickier, but you can still totally do it by inspection. It's the omega one. All right, so again, omega is 1 over t, right? And in our repeating parameters, the only one with a t is the velocity, right? And that t is on the bottom. So we know we're going to want to have b to -1, right? Because you need to flip it. You need to flip it up top. Okay, and then to balance that, you just need this d to just stay up top. So c equals 1. And a equal, and then you don't want any mass term floating around, so just set a equal to 0. So you get pi 2 equals omega d over u, right? And again, pretty easy just to do by inspection. Don't really need to do any math for it. If you want to do a math whole thing out, go back to problem 1, you can do that. And pi 3 is our force term, which we already did in problem 1. I'll say C problem 1. It's literally the exact same thing. A equals -1, B equals -2, C equals -2. Right? So you get pi 3 is F over rho u squared d squared. Okay, and we want to formulate this lift behavior as a dimensionless function. Like we did in problem 1, right? You can say pi 3 equals some function of pi 1 and pi 2. Or alternatively, if you wanted to, if we were solving for angular velocity omega, you could say pi 2 is a function of pi 1 and pi 3. They're all functions of each other. Or pi 1 is a function of 2 and 3, yada, yada. You can flip-flop them, permute them, however you want. Doesn't matter. All right? So just expand it all out. And then, like I said, if you want to go one step further, you can. You can say F equals rho u squared d squared times some function of L over D omega D over U. And boom, you're done. And like I said, you don't necessarily know what that function is, but they're all proportional to each other. So you can set them equal to each other if you need to, and solve for all the stuff. It's nice. Nice and easy. Not a very tough concept. A lot of algebra. Once it passes the first part, it's pretty chill. Cool. Any questions? All right. If anybody online needs anything, shoot me an email. It'll be cool. All right. Thanks, guys.